everyone. I want to welcome you all here. So it's really my privilege to have the chance to introduce you all to Solomon Hsiang, who tonight is talking to us about adaptation to climate change. What do the data say? I should note that this event is first for us, so it's a collaboration with two other centers, as you see up there on that rather busy slide almost. So this is a collaboration between our center here, the Center on Global Poverty and Development, the Center on Food Security and the Environment, and also the Center for Innovation and Global Health, so a real effort across campus. Dr. Hsiang's work combines data with mathematical models to understand how society and the environment influence each other. And in particular, he focuses on how policy can encourage economic development while also managing global climate. His research has been published very widely in leading journals, some of which you may even heard of, including the likes of Nature, Science, the Proceedings of the National Academy of Sciences. He earned a double bachelor's degree at MIT, one in Earth, Atmospheric and Planetary Science, and the other in Urban Studies and Planning. He received his PhD at Columbia University. He was then both a postdoctoral fellow in applied econometrics at NBER, the National Bureau of Economic Research, and he was also a postdoctoral fellow in science, technology, and the environment and environmental policy at Princeton. He's currently the Chancellor's Professor of Public Policy at UC Berkeley, research associate at the NBER. And we're really delighted that Solomon's been visiting with us here this year at Stanford all year. First as the Noosheen Hashemi visiting scholar here at the Center on Global Poverty and Development, and also as the Gloria and Richard Kushel visiting scholar at the Center on Food Security and the Environment. If you come to many of our events, you know that I often like to reveal a little known fact about our speaker, and I just pried one from Solomon just here 5 minutes ago, which I'll share with you, which is that for his fifth birthday, the theme of the birthday party was that he and all of his friends were supposed to dress up as what they'd like to be when they grow up. So his friends came dressed as things such as astronauts, firefighters, anything you might guess. Solomon dressed up as a professor. And in dressing up as a professor, he told me that he wore the same clothes that he would wear on any other day of his life as well. After Solomon's talk, Marshall Burke will moderate a discussion with him and take some questions from all of you as well. Marshall is well known to you, and I will be brief. He's an assistant professor here at Stanford in the Department of Earth Systems Science, and he's also deputy director of the Center on Food Security and Environment, and he's a faculty research fellow also at NBER. So please join me in welcoming Solomon Hsiang.
Great, it's a pleasure to be here, and I've really enjoyed spending the year here at Stanford, getting to interact with the diverse communities. Many of you I've spoken with at different meetings, and it's a delight to really share with you some of the work that we're doing with all these different teams and collaborators across the country. David asked me to speak about adaptation and climate change, and so I'm gonna try to provide a sense of a lot of empirical investigations that are coming together to help us understand how populations around the world might potentially adapt to the climate. Now, when you think about climate change, we're really dealing with a development question where there are people, billions of people around the world trying to, as quickly as possible, to improve the well-being of their families and their livelihoods, but that comes at some substantial cost. And the production of a large number of CO2 molecules, a lot of emissions, and we are standing here today at this moment in time where we have to make decisions about how much we want to invest in different types of energy sources. Now, in doing that, we're thinking a lot about the costs of those investments. The job that I have most of the time is to help people understand what are the potential benefits of traveling down these different pathways. As we look ahead, we want to make an informed decision to weigh both those costs and benefits. And so there's this economic principle at the heart of all this work, which is that the amount of resources we allocate to managing the climate should reflect the economic benefits that accrue to society from those investments. Now, the magnitude of those investments we should make depend fundamentally on the answer to this question about whether or not the climate has a large influence on society. So for centuries, philosophers have thought about this question, and there's one hypothesis that the climate doesn't matter very much, another hypothesis that the climate actually matters a great deal for the economy and the well-being of societies. And central to this question is this notion of adaptation and how adaptable populations are. If it turns out that human society is highly adaptable to the climate, then it's possible we might just cope with any changes that arrive down the road, and any type of climate change that arrives in the future will matter very little. Alternatively, populations might not be that adaptable, in which case climate changes might impose large costs on society that we'll have to bear in the future. And distinguishing between these two different outcomes requires an ability to actually measure and understand patterns of adaptation around the world. And so a lot of research now is focused on how we can do that. But it's a tricky problem because when you think about the climate, it's a very high-dimensional object. There's many ways in which the climate varies around the world and over time. There's hurricanes, there's temperature, there's rainfall, there's fires. Human society is also very high-dimensional. There's many aspects of and many different types of decisions people make every day, and those things all interact. And on top of that, there's a ton of other things happening around the world all the time that act as a confounding variable or something that makes it difficult to observe whether or not climatic factors are indeed playing a large role. So the overall empirical framework that we use when trying to understand these questions is to think about, first, what might be the ideal experiment we'd like to run. So what I'd love to do is have two worlds, right? We would change the climate of one, not the other, and then ask, how does society cope with those changes? How do they adapt, and does the climate matter, okay? That one is a hard one to slide past the IRB. So instead, what we actually do is we try to look for situations that we call quasi-experiments, okay? These are settings in which the setup sort of looks as if it were like an experiment. And so often that involves, and I'll show you many examples, reconstructing the climatological history of some location, and then following a population over time as it's exposed to one climate and then to a different climate. And then we observe how they cope with those changes and try to understand, did it affect their well-being? How did they adapt? What other changes do we see? Now this is sort of the mathiest looking slide I'll show, but it does paint a picture of sort of the whole principle of this talk, so I'll walk through it slowly. The idea that we have is that we think of the climate as some probability distribution of possible events that any population might experience. And on any given day, there's a distribution of weather events that might occur here at Stanford, and we all experience a series of realizations over time. In this graph, time is going down. So we get draws from that probability distribution, and then we imagine that there is some surface, some function that describes how societal outcomes result from those experiences happening outside. Those map on to some sort of outcome, some sort of realization of maybe how happy we are or economic productivity day over day in some sort of social measure, and that leads to a distribution of some social outcomes that we actually care about, maybe economic productivity or the risk of conflict. My job as the econometrician is to try and look at this data and back out from it these types of surfaces that tell us how changes in the climate map onto changes in social outcomes. Now, when we think about adaptation, what do adaptations mean in this type of context, in this analytical framework? Well, we think about the different types of investments, the actions that populations take in one climate that they wouldn't have taken had they been placed in another climate. Those are coping mechanisms, things they do to deal with the environment they're confronting. Now, in this literature, there have been sort of two general approaches to trying to understand how adaptation plays a role in generating these social costs. The sort of historical approach was to look for direct evidence of adaptation, to try and count it up, understand the impacts, enumerate them, and then factor that into any kind of decision-making framework. So as an example of that, we might say, well, here at Stanford, it's pretty warm and sunny, so we wear sunglasses, we don't wear ties when we give talks, and then we account for sort of what the implications of that might be. People might not take us quite as seriously, but we might also be a little more comfortable, and that makes us maybe more productive, right? You can see how it can become a rabbit hole, though, because there's many, many, many margins on which we can make adaptive adjustments, and it becomes very, very difficult to count them all up, to think about how they interact with one another, and to enumerate their costs and benefits. So that's a very difficult approach. An alternative approach is to look simply for the evidence that adaptation is occurring. Okay, so this is a bit like, so when people adapt, they adapt because it reduces the effect of the environment on them in some adverse way, or it provides them with some benefits from the environment that they wouldn't otherwise have gotten. So we can look for those changing interactions between the population and their environment and think of that as evidence that the population is adapting. And so an analogy is actually to think about the recent news about taking a photograph of a black hole, right? In those photographs that were on the cover of the New York Times, you don't actually see the black hole itself. You see the evidence that the black hole is there because it's affecting everything around it and creates this bright ring around it, okay? So we look for ways in which the adaptive behavior is distorting the response that we would expect to see. And so, approach number one is quite difficult, and so in our empirical investigations, we are always going to be taking approach number two. In the context I was just showing you, the way that adaptations will show up in this framework is the change you see here between the blue line and the pink line, okay? So if you look at the top, we have two different climates. We have one climate that's shifted to the right, maybe it's a little hotter, and so the realizations that manifest from that climate are a very different sequence of realizations. Populations might be taking different types of actions. Maybe they're doing things to protect themselves from extreme events, say. Maybe they're installing air conditioning to protect themselves from hot days. And so that changes the mapping from realized environmental events to some sort of social outcomes, which in turn then is very important to characterize when making any sort of projection about the future. So I'll show you some examples of how we're doing this with real data, which might make it more tangible, if that figure seems too abstract. So a large body of our work thinks about hurricanes, typhoons, tropical cyclones. It's all one family of phenomena, and they have massive social implications when they strike middle income or even wealthy countries, developing countries. One way we've studied them is we actually build a physical model of cyclones. And so what you see here is a surface where the height of the surface depicts the speed of winds within a hurricane. And you can see sort of the high point in the middle is the eye of the storm where the winds are most intense. And then what we do is we reconstruct the storms that have happened over the historical record. So here you see the Philippines in 1970, and this is Super Typhoon Joan passing over the Philippines. And the brighter orange colors are showing locations that are more heavily impacted by the storm. So we reconstruct all these storms, and we actually reconstruct them all around the world. So there's a lot of hurricane activity. Most people, I think, in the United States focus on what happens on the Gulf Coast, but there's actually a great deal of activity that's happening in the Indian Basin as well as the Pacific. We then construct all the storms that have happened throughout the historical record. Okay, so this is thousands of storms. And we try to understand what their economic impact is. So here we see a graph that I think is not surprising to anyone. I'm just showing it to you to convince you that the way in which we reconstruct these storms actually predicts something of economic importance. So on the x-axis here is our measure of exposure to the storms, and on the y-axis is the economic damage occurring in these two different states over recent history. Okay, so these are insured losses, and these are some of the storms we've seen. Katrina up here is way off the line, in part because the Katrina event was a really extreme event. It was not well predicted by the winds that were experienced. Most of the damages happened because of the levee breaks, which is sort of outside the scope of our model. Now, in thinking about what adaptation looks like in this framework, we can take a different measure. So now I'm looking at mortality rates during storms, and I'm looking at a country level. So here, what I'm showing you is Vietnam. And what you see is that as you increase the intensity of a storm, we have higher mortality rates. And what I've denoted here as the vertical line is just the average exposure that occurs in Vietnam. Okay, that's the average intensity of the cyclone climate there. We can look at a different location, like the Philippines. The Philippines is, on average, a more intense environment. They get many more cyclones. And what you see is the slope of this line is shallower. So when the same type of physical event occurs, it actually produces lower rates of mortality. We can then look at another location, like Japan, which has an even more intense cyclone environment, and you see a very shallow slope, okay? And that is because the country of Japan is very well adapted to their cyclone environment, and it produces much lower damages given the same intensity exposure. Now, so there's this sort of pattern where there's populations that are heavily exposed to a certain environmental condition, but it doesn't have as big an effect on them, is a very generalizable pattern. It's been documented in agriculture. It's been documented in terms of looking at people's productivity all over the country. One question is, all over the world, one question is, why does this occur? And this turns out to be a very important question in terms of thinking about how populations will adapt in the future. So one hypothesis that has been out there for quite some time is that populations live in a climate and they learn about it. And over time, they come up with little ways to tweak their life. They do things a little differently. Maybe they wake up earlier to go running if it's hot out, or maybe they take a siesta in the middle of the day. So there's lots of little changes they make that are relatively costless that allow them to protect themselves over time. And I note here that sort of this is an idea that was sort of pushed forward by Bill Nordhaus and many of his colleagues in a lot of seminal work. And Professor Nordhaus was awarded the Nobel Prize for much of that earlier this year. An alternative hypothesis is that people aren't really learning about their climate. They know what climate they live in. They only make investments in protecting themselves when it makes economic sense, when the costs of those investments are less than the benefits that will accrue from the protection they provide in the future. Now, distinguishing between these two things is really important because it affects how we think about what might happen in the future. So what we've done is we try to ask this question, how can we distinguish between these two hypotheses? Now, one of the key differences between them is whether or not learning is happening. So if what is most important is that people need to sort of live in an environment for a very long time to continuously learn about it and find ways to protect themselves, then simply just being somewhere long enough will allow us to adapt effectively. But if that's not enough, it might mean that we actually have to change the equation between what the costs and the benefits of some types of adaptation are. So how can we test this? Well, it's very hard to sort of test hypothesis 2 directly. What we can do to test hypothesis 1 is to look for some population, look for a very long time, and ask, as they accrue more experience with their climate, do they get better and better adapted to it? Okay? Now that's kind of a tall order from a data perspective, because we often don't have very, very, very long time series of data. But I did manage to find a colleague who had a really interesting one. So I have a colleague who's a historian at Trinity College, and he has encoded over a millennium of data from the Irish Annals. And this represents basically 22 texts from monasteries around Ireland, going back to the year 400, in which monks were encoding everything that was happening throughout the country on an annual basis. So we're working together to analyze this data, and just to give you a sense, this is what a page out of one of these monastic texts look like. So this is from around the year 852, and it looks a little bit like Elvish, but what that box says is, much ice and frost occurred so that the principal lakes and rivers of Ireland could be crossed by people on horseback. Okay? So what my colleague has done is we take that, he's read all of this, and we turn it into a binary variable that says it was a cold year. Okay? So then, and what he does is he then passes me this really interesting data set where we can ask, as a population experiences a certain type of climate for a millennium, do they learn? Do they learn how to adapt to that climate in such a way that they can protect themselves? And so, what you see are that some of the texts are going in and out as different monasteries open and close, but overall we have over 40,000 entries about what was happening in Ireland over this time period. We analyze things between 600 and 1600, and what's really interesting is this is a period in which you go from having hundreds of kings around, the Vikings invade, they introduce currency for the first time, then they become a colony, we throw out the empire, and then eventually becomes a colony again. Okay, so there's all sorts of institutional changes. We're going to ask, is the population adapting to this climate? And to do that, what we're going to do is match up different types of events. So, for example, here are two different events that both occurred in 1270, in which we see that there was both a very cold year and also records of famine. So we can ask questions like, what was the probability that famine occurred as a result of changing climate? So what you see here are some regression results in which I'm showing you the probability of a famine occurring, that's on the vertical axis, in response to a cold event that occurs in year 0, okay, a really cold year. And so what you see is a magnification of famine risk by roughly 25%. So there's if your year is cold in Ireland, there's a 1 in 4 chance that there's a large-scale famine. This is looking at the whole data set. What we want to do is think about whether there's evidence of adaptation over this millennium timescale. So let's think about what that would look like. Well, we have two types of years. We have normal years and we have cold years. And we see that in normal years, there's always a probability of a famine. And in cold years, there's an exaggerated probability of a famine. Now, if populations are adapting, we would hope that over time, they would find ways to protect themselves so that those cold years do not cause as much additional famine risk. Now, what I'm going to show you now is the slope of this line over time. So we can look over the centuries. On the left here, I'm showing you the probability of cold years in each century. So each bar is a separate century, and we see that overall the climate is relatively stable. We also see the probability of windy events. That's just our encoding of large-scale storms, and that's also occurring throughout the entire millennium. Now we can ask the question, well, when we throw all the data together, what does it look like as the average risk that a famine occurs? If we have a cold year, well, it's 29% above average. And if we have a windy year, it's 12% above average. Now, we would hope that if the population is learning about their environment over time, that that line will decline as the centuries progress. What we see instead is no evidence of adaptation whatsoever, okay? If anything, we basically see no statistically significant evidence of adaptation, and it looks almost as if it's increasing, although that's also not significant. In general, it's quite remarkable that we see a very stable relationship between the probability of famine as a response to these cold or windy years. And this suggests to us that there must be something else going on. It's not that the population doesn't understand their climate and is needing centuries to learn about it. It's that there's something else that's preventing them from adapting to these environmental stresses. And the last thing I'll say is that, it could be, sorry, forgot this, I put this slide in. You could think maybe they're not adapting because these things don't really matter, okay? So what I've done here is I've taken all 1,000 years and ranked them on the left by how many years were normal. Here we have all the windy years, here we have the cold years, and here we have the years that are both, okay? Now, the vertical axis here is just whatever the risk of famine is, and what you see is that there is a substantial baseline risk of famine the whole time. The area of this rectangle tells you how many famines were occurring overall in each of these years. What we can do is we can calculate what was the amplification of risk occurring in these windy years, what was the amplification of risk occurring in these cold years, and so the area of these boxes is telling you how many famines throughout Irish history should be attributed, how much famine risk should be attributed to these cold years and these windy years. And what we see is that roughly 40% of famine events across this entire millennium can be linked to the climatic events. So it's not that these, adapting to the climate didn't have an enormous human payoff if people could find a way to protect themselves from these types of adverse events. Now, okay, so that was, a millennium of Irish history. Maybe that's not relevant today. Well, there have been a bunch of other studies in the literature, including by our distinguished colleague Marshall Burke, asking the question whether or not people, even in the United States, one of the most advanced countries the planet has ever seen, whether or not populations are adapting to the climate. And so what we see is over here on the right, we look at agriculture, and we find that when populations experience very gentle, gradual warming across the Corn Belt, they still exhibit the same response. So this is showing that as temperatures get hotter and hotter, at some critical point, crop yields, particularly maize, decline quite dramatically. It doesn't matter if this occurs slowly or quickly, we see essentially the same response. In a different analysis, my colleague Tatiana Derugina and I looked at whether or not basically the GDP of counties was responding to changes in temperature. And what we see somewhat surprisingly is that as temperatures get warmer, counties become slightly more productive. There's an optimum right around the temperatures that most people find quite comfortable, and then there's a decline at higher temperatures. And what surprised us is that if you look decade over decade in the modern United States, there seems to be no change, particularly in this downward sloping side, in the structure of this relationship, which suggests that, that we're not adapting in some way that is effectively decoupling economic productivity from daily temperatures. So, stepping away from this, we think, okay, well, it's not a matter of just learning about the climate. It must be something else. And so we've started thinking a lot about what are the costs and benefits. These are the things that are really important for understanding how much we might adapt in the future and how much value it might generate to society. So, we can reflect on this. I'm going to show you one analysis in which we're really dialed into this particular problem. So this is some work that was actually supported by, I think, some folks in the room, came out of the Risky Business Report. On the left, we're looking at sort of one way of estimating total economic damage across counties in the United States. And one of the important findings is that there's this big north-south difference, where the south is suffering much more, the north, in some cases, might even benefit. And that's important, especially for inequality, because the south, on average, exhibits lower income. Now, a lot of this result comes from, sort of under the hood, the effects of temperature on human well-being and human health in particular. So what you see here is a graph in which we're showing what were cumulative damages within the United States as a function of changes in global surface temperature. And the main takeaway from this graph is that as we move to the right, the biggest thing in the room is this blue wedge, which is related to human mortality. So human life is very valuable, and so if we change the climate in such a way that mortality becomes more likely, that's a large loss of value. So we're going to focus in on thinking about whether or not populations might adapt by protecting themselves from excess mortality during extremely hot events and extreme cold events. So this is a graph that is sort of a canonical graph from this literature. Many researchers have produced things like this, where you have daily temperature on the horizontal axis and the excess mortality that occurs as a response to that daily temperature. You see that on hot days, you have higher excess mortality, and as you do on cold days. If we think about what adaptation in this context might look like, what it will result in is the curve flattening out, okay? So that if everyone's walking around in spacesuits, over time, when we have a hot day, nobody's going to suffer, right? We will all have our health protected. Similar to a cold day. Now, what's important, though, is that if this occurs, it's not going to occur for free. If we're all walking around in spacesuits, someone's got to pay for those spacesuits, right? And that's not going to be cheap. So part of our exercise is to understand how quickly these curves descend, what causes them to descend, and if they descend, how much will it cost society to protect the population. To do that, we've assembled what we think is the largest global data set on mortality at the subnational level. So what I'm showing you here are just regions of the world in which we're looking at basically county-level mortality rates over different periods of time, shown here on the horizontal axis. And we're going to do an econometric analysis of patterns of adaptation as well as excess mortality risk. When we do that, when we throw all the data together and just look at half the world's population in this one single regression, we get a relationship that looks pretty much like the U I just showed you, where on average, if you randomly sample a person, you have higher mortality risk on hot days as well as on cold days. But this average curve hides important differences around the world. So what I'm going to do in a moment is I'm going to focus in on sort of this part of the curve right here. I'm going to show you what is the effect of a hot day, so 35 degrees Celsius, on excess mortality risk for the oldest age group, which is above 65 years. So when we look at what is the effect of these very hot days on this group, we can look at locations around the world that tend to be very cold on average, and we see that they generate high mortality rates on those hottest days. And then as we travel to hotter and hotter locations, we are traveling to populations that are more regularly experiencing these hot days, and we see that the effect of these hot days is declining and then roughly stabilizes. Okay? So that is indicating to us that there is adaptation occurring because people are somehow protecting themselves from these hot day events. Now, importantly, it's not just the average climate that seems to predict how sensitive populations are. It's also whether or not they have access to resources. So high-income populations tend to be better protected. They have the resources to deploy air conditioning or better health care that is protecting themselves. And so on this graph, I'll show it over here, what I'm going to do is show you everyone in the world is somewhere on this graph in one of these 9 boxes. On the horizontal scale, we're grouping locations by their average temperature. On the vertical scale, we're grouping them by their income levels. So people who live in so down here in the lower left, we see populations that tend to be cold and poor. And what we see is that the shape of their response to hot days is very extreme. Okay, these populations have very few resources to protect themselves, and they're not exposed to these events regularly. We can go to populations that are richer, and what we see is that as populations have greater access to resources, even in cold regions, the effect of these hot days is declining because that curve is getting flatter and flatter as you move up. Similarly, we can look at hotter locations, and we see that within each of these groups, as locations get hotter, the curve also goes down, okay? Because populations are more experienced with these events, and the cost-benefit calculation of whether or not it's worth it to invest in protective investments may have changed. And then it becomes the flattest in the top right group. Okay, so those are locations that are very, very hot on average and also have a lot of resources. One reason it's important for us to think about both dimensions here is because in the future, as we're thinking about climate change, the world is going to get both hotter but also richer. And so what the little red text, which is hard to see, is that by the end of the century, by our estimates, 23% of the world population is going to be in this box up here because we'll be hotter and richer, and roughly 50% of the world population will be in this box. So we need to understand the shifts to the right from warming, and we need to understand the shifts up due to economic development. Now, in our sample, we're able to guess how sensitive populations are based on our analysis of the data that we can acquire. But there are many parts of the world here that you see are blank, right? We don't know, we don't have necessarily the capacity to understand, we don't actually, let me restate it. Governments are not always collecting the data we need to do an analysis of their population. But that doesn't mean they should be excluded from any type of calculation that tries to understand the global consequence of climate change. And so what we can do is we can take our results from the last slide and try to locate people on where they live in both income and temperature space and try to predict how sensitive they would have been had we had their data. And so that allows us to color in the map and obtain estimates everywhere where we don't actually collect raw data, but we can now include them in calculations about the future. Now what I'm going to do is show you a simulation as we roll populations forward into the next century and try to understand how their sensitivity to climate change, to extreme temperatures, will change in the future. And what you see is that, this is roughly the present, but as we move into the future, our estimate is that populations will adapt, but not completely. They will be getting richer, they will be getting exposed to higher temperatures, and so those things will help them protect themselves and will change their calculus about what is worth investing in, but we still see a fair amount of yellow and red on the map. And so it's important to understand what the costs of those deaths are, as well as the costs the population had to endure or bear in order to achieve those adaptations. If we want to think about what is the social cost of climate change, we need to think about the benefits everyone's getting from protecting themselves, but also all the resources they spent on that protection. And that's particularly important because if we're investing huge amounts of money in public infrastructure projects coping with climate change, that's money that's not going to other parts of the economy. That's money that's not going to the schools or the fire departments or being invested in other types of business activities. So there are real costs from investing in climate adaptation. And so in this analysis we've done, I won't go into great detail, but we basically use what is known in economics as the theory of revealed preference to try and put a bound on what the costs of adaptation are, even though we don't actually see all the little decisions and changes that are occurring in the economy. Okay, so populations have basically done some sort of implicit cost-benefit analysis where they realize that it makes a lot of sense to invest very heavily in air conditioning or other types of adaptation in places like Houston, but in places like Berkeley, where my office is located, we have not invested in air conditioning because someone made the cost-benefit calculation that it was not worth it. You can laugh at some of these jokes. Okay, so what this allows us to do is if we have enough observations like this, we can actually back out what are the implicit costs of these investments, even though we don't observe them directly. So what we do is in that simulation I showed you, we track those costs over time, and we try to understand step by step, year by year in each of thousands of simulations, what is our estimate for the adaptation costs? So I'm just going to show you this graph to give you a sense of how much adaptation matters. This is a simulation, the average simulation in a high emissions scenario of what we think global excess mortality risk would be if we didn't account for any adaptation benefits or costs. Now, the world is going to become much richer, and so moving up in that graph turns out to be quite important, and mortality risk falls roughly in half just due to the benefits of rising incomes around the world. We also then calculate what are the benefits that from adaptation that populations will undertake on their own. These are not adaptations that sort of the government is imposing. This is what we call sort of autonomous adaptation in the literature. But importantly, like I just said, we need to also account for the costs. So we need to think about the fact that those adaptations didn't come for free, and this black solid line is what our final central estimate is for the excess risk of mortality globally, on a global average, due to warming in the coming century. Now, this line here is a single line, and it looks quite precise, but we actually have a huge amount of uncertainty. So we do a large number of simulations, considering all sorts of uncertainty from climate models, and we see that there's a range of projections, and it's quite important for people to just appreciate the amount of uncertainty in this type of economic calculation. Here's a map where we're showing the overall mortality that we would expect to observe. So this is actual people dying in a simulation, on average around the world into 2010. And what you see is actually a pattern very similar in the United States to what I showed you for that US-specific study for very similar reasons. But now we can appreciate and understand what is happening around the rest of the world. And so similar to the US map from before, there are many parts of the world that end up being net beneficiaries. The blue regions are places in which populations actually experience a lower mortality risk because we have fewer dangerous cold days. In the red and orange regions around the world, you see a higher mortality risk because the losses of cold days are outweighed by the costs accruing from the extreme heat days. But importantly, this is only the mortality that we actually observe, and it's not accounting for the adaptation costs that we were counting in the background. And so once we factor those in, the distribution of who's a winner and who's a loser does change somewhat. So for example, importantly, the United States becomes a net loser almost across the entire country once you account for adaptation costs. Just to put these results in context, here's a graph where we compute the excess mortality due to climate change in this bar right here. And we are lining it up against many of the leading causes of death around the world today. Now, what you can see, this bar, the dark red, is showing you those direct deaths. The light bar is showing you adaptation costs. So actual direct mortality ends up being the largest cost, by and large, globally, but that's not true everywhere. So in these four bars, what we've done is we've just broken up the global income distribution into four groups. And what you see is in the lower income groups, we observe a lot of actual excess mortality, whereas in the high income groups, where most of us in this room are, there's actually on net a reduced actual mortality, but very high costs due to adaptation investments, okay? So there is a large and unequal, qualitatively unequal way in which climate changes and impacts on health will be borne by populations based on where they are located on the planet and what their incomes are on average. Finally, I just want to sort of wrap up. There are, I think, some economists in the room, and we talk a lot about thinking about carbon taxes, right? How much we should pay for emitting and causing this emitting CO2 and imposing this externality on populations around the world. So we finally now have the machinery to compute, in essence, how much every time we emit a ton of CO2, we are harming every other person on the planet, okay? And so for 1 ton of CO2, this is our estimate using a 3% discount rate of the overall transfer that is effectively occurring by imposing excess mortality risk on each one of these 25,000 subnational units around the world. And this captures all the patterns I was showing you before. It captures adaptation, and importantly, there's very large differences. So these graphs are showing you what is the cost as a function of global warming. So Sydney bears much lower costs than Delhi does, okay? And so embedded within this map are differences around the world due to the situations we've been talking about that differ between locations, having to do both with their climate and the resources that they have access to. We can add those numbers all up and think about what we call the partial social cost of carbon due to excess mortality risk. And this is essentially what I personally should be taxed for emitting 1 more ton of carbon. And so sort of the estimate most people focus on is a discount rate somewhere in the middle. This is around 3%. In roughly a high emission scenario, it's roughly $30 per ton, okay? And so that's, I don't know if it's a large or a small number, but it's roughly similar in magnitude to what the Obama administration had sort of declared the social cost of carbon should be, but across all sectors, not just looking at mortality, okay? And so this calculation represents to us a roadmap for how to think about all the different sectors and the distributional consequences and the effects of adaptation around the world, which then can be used to support regulation and policymaking in the future. So just to wrap up, thinking about some of the things we've learned recently and that I've tried to convey to you, we can now measure patterns of adaptation using data, and we don't have to just speculate about it. We can actually go to the data and see what's true and test different theories. A generalizable fact is that populations that tend to be exposed to extreme events often make some sort of investments that protect themselves from those types of events. But it appears that it's not historical experience alone that matters. There must be some sort of cost-benefit calculation in which adaptation is seen as a net benefit, and its benefits outweigh its costs. Those costs themselves cannot be directly measured, but we can now have approaches that allow us to implicitly measure them and keep track of them in calculations that can now be quite rich and allow us to account for both the benefits and the costs at a granular scale in support of policy. Thank you very much.
All right, so while we're switching this, I'm Marshall Burke. I'm the Deputy Director of the Center on Food Security and the Environment, and it's great to be here. Saul's actually a longtime co-author of mine, and what's always embarrassing in these sorts of settings is I learn much more than I should let on from hearing him talk about work that I've seen presented many times, so it's always nice to see. So while you're thinking of your questions, we have about 20 minutes for discussion. While you're thinking of your questions, I'll ask a couple warm-ups, and maybe I'll skip what were going to be my funny ones. So I'll start with one. So you showed a lot of really interesting evidence on adaptation across a lot of different domains, right? Everything from the Irish way back when all the way up till the current day. And one thing that's striking to me in looking at that is you see a lot of heterogeneity in people's apparent ability to adapt, right? So you showed the Irish setting where it looked like you weren't seeing much adaptation at all. You showed the US agricultural setting similarly where we don't see a lot of evidence of recent adaptation. And compare that to the hurricane setting where Japan gets hit by a hurricane and is hardly hurt, or rich places in the US or do not appear to experience high mortality when it gets hot, right? So do you have a generic sense or some sort of sense of what explains this variation? Why do you see adaptation in some contexts and not in others?
So what I said at a very high level is that the benefits have to outweigh the costs. But there's some nuance to that. So it has to be the perceived benefits outweigh the cost and the perceived costs. And so one thing that that's in the 60-minute version of this talk is that when you look at hurricanes, for example, we see people adapt very well to physical damage and observable immediate mortality. So those are things after a storm comes through, you see in the newspaper headlines about sort of how many people died and what the damages are. What we've also documented is that there's large reductions in economic productivity that occur in the many years after a storm. And that actually becomes much harder to observe because most people are not as aware of foregone earnings that they didn't earn this year because of a hurricane that happened 5 years ago, right? That's a much more difficult thing cognitively to track. And what we see is actually no evidence of adaptation on that margin. And so I think one take home from that is that there are certain things when a storm comes through, we see the buildings fall, that's very salient. We design regulations to protect the buildings or to protect the populations, but then things that are sort of quieter damages, we'll call them, sort of that occur sort of in a subtle way, those things get missed and populations seem to be bad at adapting. The other thing that really matters is technology, and that's something I didn't talk that much about. But in many cases, the reason the cost-benefit calculation doesn't make sense is because there exists some technology to adapt, but it's just too expensive to be worth it. So, we all could, in principle, walk around in spacesuits all the time right now. Spacesuits exist as a technology, but it's just not really cost-effective to be doing that. And so there's a whole bunch of things that go into that calculus, and I think we're trying to figure out which constraint is binding in which setting. I think that's a really important thing from a policy perspective moving forward, because the role of the policymaker could be to try and sort of loosen those constraints by either fostering innovation that will bring the costs of adaptation technology down, or by helping populations feel sort of some of the more subtle impacts as something that is more salient. So there's lots of margins that could be leveraged.
So follow up to that, do you own a spacesuit? And if not, why not?
It is expensive, but I
So
hope
the
to.
benefits have not exceeded the cost.
The price.
You'll buy one soon.
Yeah.
Okay. So we're at CEPR, right? A bunch of economists, and economists are historically very bullish about adaptation, right? And so when you give talks like this, I think what you likely often hear is something like the following. So historically, we've seen half a degree of climate change, maybe a degree if you start from pre-industrial. So that's not that much. Maybe prices haven't changed that much. Maybe we haven't noticed in some settings. But in the future, we're going to see 4 degrees, 5 degrees Celsius, right? So we haven't adapted historically, but that's not a good guide for what's going to happen in the future, right? We're going to see a much bigger shock, and we're going to figure out how to deal with it. What do you say? What would you say in response to your economist interlocutor?
I think this is a very common question. It's a really important one. I think projecting trends in technology is fundamentally challenging, and I think I think people are all over the map on this. One reason we actually started looking at that Irish data was because we thought, well, these guys, they've faced this climate for a long time. They must have innovated. They must have come up with ways to protect themselves. We actually even know that at the time they had ways of storing grain for long periods of time to avoid famine, but it just didn't make economic sense to do it because basically, preparing for the future, adapting actually requires you make investments that benefit you in the future. So we often, for example, hear that we're not making investments to protect ourselves from climate change because we don't value the future enough. But actually, the exact same logic is why you would adapt, right? Because you would make an investment today to protect yourself in the future. So I think that's an environment in which we expected to see more innovation to occur, and it turns out that that was not the thing that was preventing people from adapting. Moving forward into the future, I think we will probably innovate more than we have, but I'm not sure that most of the global population will have access to those innovations. So most of the world today, lives on much lower incomes and doesn't have access to the technological frontier when it comes to computing or cell phones. I mean, they have access to some type of cell phone. They have some access to some type of seed, but it's not always the best available. And so I think trying to understand, what are the obstacles to technological diffusion are essentially, relevant to this exact problem.
Great, so let's open it up. We got 10, 15 minutes. Love your questions. So maybe stand up, you could state your name, and got a mic going around. So yeah, in the back.
Hi, my name is Maya Dorado with King Philanthropies. I have a question on the graph that you showed with the projection of mortality in 2100. And you said that part of the reason that those mortality rates would be lessened is, projection of rising incomes and overall wealth levels. What's the risk that climate change itself interrupts that growth and their ability to adapt?
That's a great question. In some work with Marshall Burke here, we've tried to study that question, and there is a fair amount of evidence that warming can lead to accelerations in growth if you're a very cold location. So, for example, regions of Canada might actually experience heightened growth rates due to warming, but most of the world is hot enough that warming is expected to reduce growth rates. And so that is not factored into that graph. Now, that would have two effects. One is that it changes people's ability to protect themselves. If growth rates are lower, fewer people will move into the higher income groups. But it also changes how the trade-offs we observe people to make in terms of valuing human life. And so in general, we observe that people spend much more to protect human life when they have more resources available to do that. And so that would enter our calculation in one way to increase the cost, but also in one way to decrease the cost.
All right. Sure, other folks have someone's over here. Yep.
Hi, I'm Laura, and I work with Steve Luby in medicine. I was wondering, well, I was very disheartened to see the graph where the greatest mortality burden is mostly in Africa. And I guess it brings to me the question of who needs to feel the costs and benefits in order to do something about it. It looks like most of Europe, and you said there are some effects in the U.S., but things aren't terrible. And those countries maybe don't feel the costs and benefits that would need to be felt in order to help people in the places where it will be felt most, like in Africa. And so I guess it's a long way of saying sort of how do you factor in governance structures, given that a government minister might not feel the effects of climate change because his family has air conditioning, and he is not responsive to the needs of his people who do feel those effects. So it's sort of a disjointed costs and benefits.
So you raise a really important question, one that we do not explicitly include in these types of calculations. It's more of a political economy problem. I think it's really important that both individuals and decision makers have a sense of what the actual impacts might be so that they can make better judgments about, to take care of their populations. Of course, ultimately that depends on having a governance mechanism where sort of that kind of welfare maximization is actually occurring. I think we're not there yet in many countries around the world, including in this one. So, for example, we've done some calculations of, what did Hurricane Maria do? What will it probably do in the future to the economy of Puerto Rico? And by our estimate, for example, Hurricane Maria probably undid about 1 to 2 decades of economic development in roughly 12 hours. Our projection is that it will reduce long-run output in roughly 15 years by about 20%. Okay, and so and Puerto Rico has a pretty slow growth rate. So that's a context in which we've been trying to get folks to pay attention to that issue and say, if you don't help rebuild, this is going to be something that's going to be taxing on the population for quite some time. And some parts of the government have been very receptive to that, and providing that information alone was enough to mobilize important resources. Of course, it wasn't enough to do sort of the full recovery that I think many people would like to see.
Up front here, yeah.
The studies seem to be very country-oriented, and its effect on people in countries. What about mobility as climate change occurs? That a country unit may not be relevant at all, and so your maps may look entirely different if you incorporated the natural migration that would occur to people to leave those areas and go to better areas.
That's also, you guys are all nailing the great questions. I glossed over human migration, which is sort of a really important question and a really important way in which we expect populations to cope in the future. We have a lot of active research on that exact question. How will people mobilize? Who will mobilize? Where do we think they might go? And why might they go there? That's important both for those populations who are themselves at risk, as well as populations that are potential receivers of those populations. There's a lot of, once you start going down that road, there's a lot of questions we ask. We know in this country, we've had experience, the Dust Bowl caused basically an evacuation of the Midwest, and populations moved into cities, labor markets became very crowded, wages fell. So we ourselves have experience with those types of events. It turns out to be a very difficult problem to crack using sort of rigorous quantitative approaches, in part because data quality for tracking people around the world, particularly in the regions that we think are most likely to produce migrants, is the data quality is very low. And so we are working actively on that, but I think that's really where the research frontier is today.
Time for a couple more over here. No?
It's a related question. So your work is very data driven, and it's great because there's more and more data becoming available. And what is your dream about, like what kind of data are you waiting for to come out for the next 10, 20 years that you can analyze?
It's a great question. I've never thought about it. I generally feel like we have far too much data. We just don't have enough people to analyze it, is what I tell people all the time. So I don't usually, I mean, migration data is really, really hard. I'm not sure we're actually going to get it, but I will think about it. That's a good question. I don't have a good answer.
All right, stumped him. Good.
So yeah, we in an effort to deal with the paucity of population-based data historically in many parts of the world, we have a big project right now that I spoke about with another group, where we've recovered. We're working with an organization in the United Kingdom. Basically, after the World Wars, the British Empire had lots and lots of spy planes that they didn't have anything to do with them, so they sent them around the empire to survey the colonies. And so now we are working with a team to digitize, stitch together, and extract information from roughly 2 million aerial photographs taken over the last century from around the world. And hopefully that will let us tile together some information on where populations were in regions like Africa, where there's very poor municipal records. And so we're trying to fill in the gaps with data. This is what I'm saying. Like we can't get the data. There's literally robots in the United Kingdom scanning the images right now. We can't do it fast enough. We have so much data, and we just not enough ways to analyze it.
All right, one or two more here.
On St. Bridget's Day, now called Groundhog Day, and then they made decisions in their family unit as to how much food everybody was going to get for the remainder of the winter period until crops came in. So, but my question really relates to, so you may want to look at that in the future.
That's fantastic. I would love a reference to that.
Yeah, and so, but you may want to also look at crop data because there will be a lag for the efficiency of crop data related to population survival. And I'd love to hear a comment on that.
Yeah, so in that analysis, we do look at agricultural production and agricultural, I just didn't show it because it was a short talk. We actually even have records. I mean, we have evidence that populations were adapting, in part because one of the things that the monks in the monasteries recorded was whether or not there was widespread wild animal mortality. So some of the records would say, like, all the deer in the forest died. It was so cold. And so what you actually see is that the wild animal mortality rates are much, much, much higher than the human mortality rates, in part because humans are doing a lot of things to protect themselves and insulate themselves more effectively than wild populations, but we see that essentially over this long period of time, the pattern of how coupled human well-being is to the climate is not changing. So whatever actions they were taking, and that reference you have is really interesting, they just weren't innovating in such a way that they were continually improving and continually protecting themselves over this time.
Last question up here. I think there's one more. Yeah? Got a mic coming.
Let me make a series of comments and ask you to comment on them. I say, first of all, is the climate changing? And I am impressed with the science, but never mind. There is a new ocean being created in the Arctic. It's getting bigger every year. In other words, there's not only warming, but it's accelerating. The ice cap over Greenland is melting fast and faster all the time. That's observable fact. The reefs, coral reefs around the world, the Great Barrier Reef, the reefs in the Caribbean, are all acidifying as a result of the warmer ocean. That has a major effect on the fish supply. Not only fishermen, but people who eat fish, which is a lot. So these things are happening, and they're accelerating. So I say to myself, what should we do about it? And the evidence all in the reasoning is that CO2 is basically the reason. So I'd say, well, let's put a tax on it. Make any energy that you use pay its full cost to society. So it has a price. But added to that price, put on a revenue neutral carbon tax. I want a tax because you just put a price out there and let people use their ingenuity to figure out any way to avoid it. But make it revenue neutral so it's not a fiscal drag on the economy. And distribute the revenue equally to everybody with a social security number or something like that. So it's a progressive tax.
Maybe just in the interest of time, would you like him to evaluate your policy proposal? Thanks.
I'm on board. I'm totally on board, and I think a lot of the work that we're doing is trying to put a foundation on what that tax ought to be, to have a very clear line of sight from the data to the policy prescription for exactly what the tax should be, because there's lots of taxes you could pick from, and it's actually a very important calculation to make sure we get something that's near what the actual social cost is. We don't want to tax too much, because then we're going to be taking away resources from other investments we should be making. We don't want to tax too little, because then we won't be investing enough in the climate. So actually understanding what the tax should be and grounding it in real-world data is, I think, a fundamentally important exercise and completely consistent with the policy you're proposing.
Getting less expensive and lots of batteries the same. That's not an accident. That's the result of R&D. And so that should be encouraged. And the government's amount of money, say at Stanford, is minuscule. The private funding is 3 times the government funding. In other words, private people see something happening and they want to know about it, and they come and they pay. So good support for energy R&D is a very important component. Sorry about that.
No, it's a good point. Well, with that, maybe you can join me in thanking Saul for a great talk.